Okay, so the two announcements are, on Wednesday, we're going to do a computational activity. So please remember to bring your laptops ready to work with Python. And then this week's office hours are going to be handled by our TA, Luis. He can be found in the 1515 room here in the engineering building, in the CMSE fishbowl. If you've ever been there, you know what that means. Okay, so let's see where we are. So thus far, what do we have? So we have this idea of perhaps an ambient metric space where everything is happening. Right, so ambient metric space. And again, this can be something like Euclidean space, or the space of images, or the space of sounds, or whatever your data lives. And then inside your ambient metric space, you have the data set that you have collected. Okay? And then thus far, we have sort of two ideas. The first idea is that we can, let's say first, we can approximate the, I want to put quotation marks here, the underlying topology of X, of the data. And by underlying topology, I mean sort of the space that seems to sort of underlie the data. Or in other words, if you think of the data as being sampled from some ground truth, so from some continuous ground truth, then that's what I mean. Sort of the space that underlies the data that you collect. Okay? So we can approximate the underlying topology of X via simplicial complexes like, you know, the Rips complex of the data or the check complex of the data. So here we have Rips, here we have check. Okay, so we've seen that each one has its advantages. So for example, here we have that this is good theoretically. So we have baby nerve lemma. So there is a plus. But its computation, at least in Euclidean space, involves, so computing, and again, this is for X inside RD. So computing it for X inside RD involves this problem of the smallest enclosing ball, right? That we saw is sort of computationally difficult. So this is big O of d plus 1 times d plus 1 factorial times n, where n is the number of points in the simplex you're trying to check. So this is bad. The Rips is easy to compute. But the theory is hard or harder. So what we usually do is we use that the Rips is contained in the check, and this is contained in Rips to alpha, to combine sort of the theoretical guarantees we have for this guy with the computational efficiencies we have for this one. So we usually compute stuff with the Rips and then try to infer theoretically from check. That's usually how the business goes. So that's the first thing we have. I would like to remark that the RIPS and the check are not the only options. There are tons of other suggestions in the literature. Um, so let me just mention a few. Um, so other options for K alpha include the witness complex. This is work by Vin de Silva and Gunnar Carlson. There is also the tidy set. This is by Afra Somorodian and Gunnar Carlson as well. There's the alpha complex. This is by Herbert and Sbrunner. And there are a couple more that are around, but all in all, these two complexes seem to be the things that we use the most, at least nowadays. Okay, so that's the first step. The first step is that we can approximate the underlying topology of the data using reconstructions like these complexes. The second thing that we've seen is that we can measure the topology. I'm going to use the word shape of whatever simplicial complex we're using to do the approximation. And we can do it via these invariants that we have constructed. So we have invariants like the Euler characteristic, we also have the Betti numbers. And we also have the homology of the space. And what we've seen is that even though the Euler characteristic is defined as a counting mechanism in terms of vertices, edges, faces, and so on, it's actually closely related to the Betti numbers. In particular, the same count, sort of the alternating sum of the number of simplices can be recovered as the alternating sum of the Betti numbers. And the Betti numbers are, of course, the number of z's in homology. So in that sense, this is sort of the bigger invariant of the three that we've seen. We also saw some examples where the Euler characteristic was enough to distinguish between the shapes. In some cases, the Betti numbers were sufficient when the Euler characteristic failed, and then you had to go even further for other spaces up to the homology of the space when the Betti numbers and the Euler characteristic failed to distinguish them. Okay, so that's what we have thus far. So the last comment is the question of this choice of alpha. Right, so varying alpha. So as we said before, these complexes give you a reconstruction of the underlying topology at a particular scale. But there is just no a priori reason for you to have chosen the right scale to begin with. So the question is, what happens as you vary the scale of the reconstruction? So at least for the Euler characteristic, we have the so-called Euler characteristic curve. And what we saw is that they can be useful in classifying things like shapes, geometric shapes, and things from cosmology, to study sort of background radiation. The other element is that if we vary alpha and we compute the Betti numbers, then we get these Betti curves. And we saw at least one application to neuroscience where these Betti curves were used to sort of think about the geometric arrangement of neurons in the brain. But not only the sort of their placement physically, but rather the sort of the firing patterns. And then I guess the question I have is, what happens when you vary alpha but compute homology groups, or compute the homology of the space? This is what is called, or at least an initial version would be what is called persistent homology, and this is what we're going to start thinking about today. So I'm going to put here persistent homology. What is different about these two guys and this guy? What is different is that these are only numbers. So these are very simple things to study. You just get a function. In fact, these are integer valued functions, right? So it's just very easy to just look at them. These are a little bit different, right? Like this can give you things like z cross z2. So studying them requires a little bit more finesse. That's what we're going to start doing today. So the first step is going to be this question of how do we compare the homology of different scales. So that's the first ingredient. So comparing homology. How do we do that? Okay, so we get a bunch of, so if you vary k, if you vary alpha, you get a bunch of simplicial complexes, okay? We do know how to compare simplicial complexes via simplicial maps, okay? So let's just remind ourselves what that was. So I'm going to fix K and L via simplicial complex. I'm going to let F from K to L be a simplicial map. What that means is that if you look at how F acts on a simplex, then it essentially gives you a simplex entirely determined by what the vertices are doing. Okay, so it's completely given by its values on the vertices. So I wanna remark two things. The first thing is that here you have n+1 vertices. When you look at this set over here, this has at most n+1 elements, right? Like there's no reason why all of these have to be different. So the first remark is that the dimension of f of sigma is always smaller than or equal to the dimension of sigma. As simplicial, as simplices, right? So this is an n-dimensional simplex because it has n+1 vertices, and this is, a simplex whose dimension is at most n. It can be less if points get crushed together because this doesn't have to be injected. So that's the first observation. For the second observation, let's say that let's fix orientations on K and L. Okay, so fix orientations on K and L. So it will be useful to do the following. So I'm gonna let's U through UN in K. So we've always written a simplex as a set, okay? But once the order is fixed, saying that this is smaller than the next, smaller than the next, and so on, we're gonna write this n simplex as these n plus one tuple, right? And this is to indicate that these points have been ordered. So to indicate the order. Okay. Now, if I apply my f, right, my simplicial map to this simplex, right? So f applied to u0, u1, un. So it's of course given by its values on the vertices. Okay. But the thing to keep in mind, to be very careful about, is that now this is a simplex in L, correct? And then this has a particular order of its own, right? And it doesn't have to agree with the order of the U's. Okay? So this may be, some sort of VJ0, VJ1, VJN, and the J's, again, J0 through Jn, do not have to be in order. In other words, the orders between L and K do not have to be compatible with the simplicial map F. Okay? So that's the first observation. So here's what we're going to do. We're going to think about this collection of indices, J0 through Jn, as a permutation. Okay? We're going to think of it thought of as a permutation. Right? So for example, this can be 5, then you can have 3, then you can have 7. So it's some permutation of n plus 1 numbers. So given this permutation, we're going to define the sign of pi is going to be the number, it's going to be -1 to the number of inversions of pi. And I'm going to explain what this means. And I think it is easier to do it with a particular case. So for example, so let's say that my permutation pi is 0, 1, 3, 2, and 4. Right? So say that that's the permutation I'm given after I apply my simplicial map. Now, an inversion is swapping 2 of the elements, right? An inversion is swapping 2 of the elements, And the number of inversions is the number of swappings that I have to do to put this in order. Okay? So to put this in order, I have to do one inversion. Namely, I have to swap 3 and 2. So that's one inversion. So the number of inversions is 1. And then the sign is minus 1 to the 1, which is minus 1. Okay? So now we have everything we need to move forward. Again, the first element is this idea of simplicial maps, which are functions from one simplicial complex to the next in a way that is given exactly by the action of the vertices. The second element is this idea of orientations, that if I have simplicial complexes K and L that are oriented, then when I apply my map F, my simplicial map F, the orientations, the orders do not have to coincide. So I have to keep track of how many inversions I have to perform so that the order agrees. Okay, so that not agrees, but so that the order is compatible. Okay? So now we can define the thing. So here's the definition. So let F be a simplicial map between oriented simplicial complexes it sounds too strong. So let me explain what I mean by that. So when I say oriented simplicial complexes, the only thing I'm saying is that each simplex has been oriented. That's all. There's nothing to do with the spaces being orientable. There's no sort of agreement between the orientations in any way. I'm just saying that the simplices have been oriented. Okay? So simplicial maps, simplicial map between oriented simplicial complexes. And we're going to define F sharp from the n chains of K to the n chains of L. So this is called, so sharp for music, so F sharp. This is going to be a linear map. It's going to be the unique linear map satisfying um, so F sharp of U0 UN. And let me write it like this. It's equal to sort of plus or minus this is difficult. No, maybe not. Let me I'm gonna do this here. And plus or minus this is if the dimension of this guy, this is sigma. if the dimension of sigma is the dimension of f sigma, and then 0 else. And here the sign, either plus or minus, is going to be the sign of the permutation. Sort of, let's call it the orientation permutation. Right, so this pi that I defined over there on the right. Right, so if I think very carefully about the orders, then when I apply f to this simplex, I may get it in some other order that requires some transpose, some inversions to put it in the right order, and that is going to be the orientation permutation that we have here. So it's going to be plus or minus depending on whether or not I need an even number of steps or an odd number of steps. Okay. So let's give a couple of examples just to get our heads around this definition. Yeah. So let's start with a couple of examples. So the first example is actually the one that we're going to use, is the simplest example that one can think of, and the one that is going to be the most useful throughout the course. So the first example is when we have that our simplicial complexes are in fact contained into each other like that. Okay. Right. So this happens, for example, when I have Reeves complexes at different scales. Then we have a simplicial map. Right, just sending sigma to sigma is a simplicial map. Let me call this iota. Right? Just send a simplex to itself. That is an honest to God simplicial map. And it's called the inclusion of K into L. Right, so iota is called the inclusion map. And then iota sharp from CNK Z is also the inclusion, right? Right? In the sense that, what are the guys that I have in here? Those are N chains whose simplices live in K. And since everything that lives in K also lives in L, and the map is the inclusion, then this is sending an N chain to the same N chain. In that sense, that is the inclusion. So that's sort of the simplest example we can have. Let's give ourselves an example that is a little bit more challenging. So here it is. So here's K, and here's L. And here's going to be my F, and I'm going to orient it as follows: U0, U1, U2. And I'm going to orient this as V0, V1, V2. But now let me tell you what the map does. So I have here U0, U1, U2. So U0 is going to go to V1, U1 is going to be to V0, and U2 is going to be to V1. Okay, so that's what F does on the vertices. And let's check what it does to the other simplices. It sends U0, U1, right? It sends it to V1, V0. Okay, so right there we are seeing how the orientations can be flipped. It sends U0, U2, for example, U0, U2 to the vertex V1, so it collapses. Okay, and then the entire simplex 0, 1, 2 is being sent to the edge V1, V0. So that is F. It's an honest to God simplicial map. Now let's try to think about, again, how the orientations are working out. Okay. So let's take, for example, again, 0, 1. So what is F sharp of U0, U1? Right. So again, it is helpful to think of it in terms of oriented simplices, like that. So if you think of terms of oriented simplices, then F is sending this to V1, V0. Okay. V1, V0. And then you need one inversion to put it in the right order. Okay. So this is equal to minus V0, V1. You may be sort of irritated by my change of notations between curly braces and square. Sort of, yeah, it's sort of this inconsistency between simplicial complexes being thought of as collections of sets, sort of curly braces. But once you put an orientation, you want to make sure that the order is sort of kept throughout. So that's where these sort of square brackets come in. And it's just, I think it's just useful to at least do it once to disentangle what the signs mean. Okay? Because if I did it just as a set, this would be the set V1, V0, which is the same as the set V0, V1 as sets. But having the orientations explicit is helpful. Okay, so let's now compute what the boundary, what the F sharps look like in each one of the dimensions. Right, so here is C0, K, Z, Z0, LZ. So this is F sharp right here. Notice that here in the definition of the sharps, I'm doing it in a particular dimension of n chains, and that dimension is not reflected here in the notation. If you wanted to be careful, you would add an n somewhere in here to indicate that this is the sharp for dimension n. But let's not get bogged down by notation. So okay, so for n equal to 0, this is a simplicial map from here to here. So what it does is it takes a zero chain. So a zero chain is something that looks like M0 U0 plus M1 U1 plus M2 U2. And it returns M0 because it's linear plus M1 F sharp U1 plus M2 F sharp U2. So again, here when we defined it, we said as the unique linear map that satisfies some property. All of that is to say that we define it on the simplices and then extend it linearly to all the chains. Okay? And that can be done in just one way once you fix the value on the simplices. At any rate, so now this is equal to M0 times, so F sharp of U0 is V1. U1 is V0. And the last one is V1 as well. So this is equal to M0 plus M2 V1 plus M1 V0. Okay, so that's what the sharp looks like in dimension 0 at least. Okay, now let's use this computation to do dimension 1. Are there any questions? Yep.
So the zero chain map.
Mm-hmm.
They don't map spiral.
What do you mean by that?
I guess.
So, yes and no. So, yes, in the sense that they are given that, I mean, you can investigate where, let's say, U0 goes, and then once you have all the vertices determined, that tells you where all the other higher things go. So in that sense, I would say yes. Yeah. Why do we do that? We did collapse to an edge. 2 vertices. Okay? It's because I changed the orientation of U0, U1. U0, U1 is going to V1, V0. And then it's collapsed. Yeah. Just a little bit of trickery to make the example a little bit more complicated. Yeah. Okay. Let's see dimension 1. This is the one that is interesting. Okay, so we are looking at F sharp of M0, say U0, U1, plus, what's it here? Plus M1, U1, U2, plus M2, U0, U2. Okay, so the first step is to use that all of this is linear, so we take out all the M's. So M0, F sharp of U0, U1, plus M1, F sharp, U1, U2, plus M2, F sharp, U2, U0, U2. Okay, cool. Now let's investigate what these guys have to be. So 0, 1, as we said, over here, goes to minus 0, 1. So this is minus M0, V0, V1, plus U2, U1, U2 goes to what? U1, U2 goes to 0, 1. So this is, and then 0, 2 goes to 0. So that's it. Okay. So, and again, all of these, if you want to think of it that way, all of these can be written in terms of matrices, integer matrices, right? Because we have that the guys in here can be thought of as vectors. The guys in here can be thought of as vectors, and the f is constructed to be linear. So this can be represented via a matrix multiplication if you wanted to. Okay. Cool. So just to summarize. Yeah. Correct. Yeah, so here for U2, U0, U2, since both of them go to V1, then I've collapsed the dimension. So it's 0. Right, so to summarize, start with a simplicial map, put orientations, and then just apply the simplicial map and decide plus or minus 1 depending on the sign of the permutation, and then 0 if you collapsed dimensions. That's it. And you can write all of these as a matrix if you wanted to. Okay, so that's how you take simplicial maps and turn them into maps at the level of chains, linear maps at the level of chains. Um, let's reason about boundaries and how simplicial maps and the sharps that they induce play out. Okay, so again, we start with our simplicial map from K to L. So we can do two things. The first thing is to look at the chains of K and what the boundary maps do. Okay, and I'm going to put a K in here just to be very clear that that is the boundary for K. We can also look at the chains of L. And we also have our boundary maps, but now for L. And we've constructed this sequence of sharps that go this way. And as I said before, even though I'm using the same letter here, F sharp and F sharp, hopefully it is clear from the context what is the dimension of the chains that I'm operating on. So the first question to ask when you look at a diagram like that is, does it commute? In other words, is it true that going right and then down is the same as going down and then right? Okay? And what is in fact the case is that the diagram is commutative. In other words, if you do F sharp of delta and K, that is exactly the same as doing delta and L of F sharp. We'll see in a moment why this is important. It is. Yeah, so I started with a general simplicial map. I took the sharps that the simplicial map induces, and my claim is that this diagram always commutes. Oh, I see what you're saying. If you start with linear maps from here to here and from here to here, there's just no reason for them to be compatible in any way. But we started with something that comes from a simplicial map. So that was going to give us a little bit more control.
Well, I'm saying those F sharp are just
I mean, remember that the simplicial maps make sense at the level of simplicial complex sense, right? Once you're here, these are chains. These are chains, correct? Okay, so let's see how these plays out. Okay, so where do I start? At the beginning, hopefully. So it's enough. Okay, all these maps that I have here are defined to be linear. It is enough to check that this equality holds for simplices. Right? So if I take a simplex in here and track how it moves, that should be enough to establish the result, because if it holds for a simplex, then it'll hold for linear combinations of simplices. So we're going to let sigma be an n simplex in K. And we're just going to compute what we have there. Okay? So let's start here on the right-hand side. So if we do F sharp delta n K of sigma, then what is that? So this is going to be F sharp of the boundary map on sigma. So that is the sum over j of minus 1 to the j times u0. I remove uj and then un. And then if I apply f's here, then up to a sign, this is essentially and I'm being sort of sloppy with the notation. There are two things to keep in mind. So if there are sort of two things to keep in mind. The first one is whether or not these has repeated elements, right? In which case it would be 0. And the other thing to keep in mind is sort of that there is a sign hovering outside, sort of whether or not I'm replacing whether or not the orientations match. But let me address the problem of repetitions. So there are three cases to think about before we do the right hand side. I mean, the right hand side is not that bad. So you're doing f of f sharp of u0 through un. And then this expression, it depends on what we get here. So so there is sort of a case one, and is that the dimension of f sigma is equal to the dimension of sigma, right? So in that case, there is just not much to do, because f sharp of un is going to be the same as the L of f u0 un, f un. Again, up to a sign that we have to be careful about, but it'll work. And this is just the sum from j equals 0 all the way up to n of minus 1 in f0 . So this looks awfully similar to what I have here. Okay, and that happens if all of these guys were different to begin with. Okay, so if the dimension of f sigma, if the dimension of f sigma is equal to the dimension of sigma, then in particular, all of these guys are also different. So in fact, this would be that and this is that. So case one is sort of easy. Let's see what happens when the dimensions get reduced and see what happens. Okay, in the second case, let's say that the dimension of f sigma is just one less than the dimension of sigma. So I repeat two entries. Okay? And this is the thing that I'm going to sort of the inequality from the equality from here to here is the one that I'm going to analyze. Okay, so let's suppose that the dimension of f sigma is like that, right? So in particular, it must be the case that let's see it over here. Okay, imagine that sort of u0 and u1 are the ones that are repeated. So u0 equal to u1 when I apply f. Okay, so when you're looking at here, right? So f0 and f1 are equal. So this will be 0 unless I remove either 0 or 1. Okay, I'm going to say that again. Say that 0 and 1 are the ones that repeat. Then if I remove, let's say, this u2, if I remove that, then 0 and 1 would still be there repeated. So these would have to be 0. Okay? So the only way I'm going to have some ends that count is if I remove one of the two that are repeated. So in other words, there is some j between 0 and n such that delta, we apply delta, yeah, so that f sharp of delta nk of u0 un is only the jth term where I repeat, and let me be careful here. So say that I have it like this. So uj minus 1, and I remove uj. Okay? And then let's say that uk, sort of later on, when I have uj minus j plus k minus 1, and then I have uj again. Right? So these to say that, so there is some j and k, right? So that the jth position, I have uj, and then the j plus k position, I also have uj. So those are the two that are repeated. And here, I first remove the first uj that I have, and in the second line, I'm going to remove this guy. So this is plus minus 1 j plus k, 0, yeah. If u0, if uj minus 1, if uj, I leave these as s, and then I remove this guy. Okay. So in all other instances, I'm going to get, if I don't remove either this or that, I'm going to have repetitions, and then they'll be 0. So the only summons that are going to survive is when I remove one of the two repeated terms. And then what I'm going to argue is that these guys have to cancel out. Do we see why? Maybe does it help if I change braces by squares? Maybe, maybe not. Okay. What is the difference between this and that? In different places. So here the uj is in the jth position, and here the uj is in the j plus k position, or j plus k minus 1, no, j plus k position. Okay? So how many transpositions do you need to do to move this guy all the way from here up to here? Was that? Okay. K minus 1, right? So that's the counting argument is checking how many inversions do I need to turn this ordering into that ordering, and then the k's are going to work out so that these two quantities cancel out. So that's the argument. So that makes this side 0. This side over here makes it 0. Now, if you look at this other side, if you look at the other DNL composed with F sharp of U0, Uj minus 1, Uj, Uj plus K minus 1, Uj, Un, right? Then this is 0 to begin with because you have these two guys repeated here. So this is just DNL of 0, which is 0. Okay. So in case 2, when the dimension is less than 1, both sides give you 0, therefore they're equal. And in the last case, is when the dimension of f sigma is less than or equal to the dimension of sigma minus 2. And this is the easier case. The reason why it is the easier case is because if you look in here, right, if you remove, so that, I mean, this is saying that there are at least 3 entries that are repeated, correct? At least 3 entries that are repeated. So if you remove one of them, you still have 2 repeated, and therefore these will be 0. And on the other side, we'll have something similar to this case. Instead of 2 repeated guys, I'm gonna have 3. So F sharp cancels out, and the same thing happens. So this will be a 0 equals 0 type of case. Yes.
The only reason it's 0 is because it has to satisfy the law where things
Yeah, so let's remind ourselves how we defined the sharps. The sharps were 2 cases. The first case is plus or minus evaluating f on the vertices. And the plus or minus was identified by the order, by the sign of the permutation. And you have to also satisfy that the dimensions were the same. If the dimensions go down, it's 0. So the 0 is because the dimensions are going down.
what's the argument that you using to say that F sharp of those things?
Yes, okay, yeah, because again, that's the definition of F sharp. I'm saying that if this was if when I apply, I see where the confusion is. Let me make this right. So these are different to begin with. When I apply f, when I apply f, I get that I have an fuj here, as I should, and then I have fuj plus k minus 1. And here I also have an fuj, meaning that fuj is the same as fuj plus k. Then now I have repeated terms, and now this is 0. That is the sharp. Yeah. No, thank you for the comment. And now this is delta n L of 0, which is 0. Right? It's just it was a notational blunder. It wasn't the case that these two were equal to begin with. That was not correct. What is correct is that once you apply f, you may get repetitions. And if you get repetitions, then that goes to 0 in the sharp. And then a similar argument holds here, because you have even more repeated things. You don't have to worry about this argument right here. Okay? So we've shown that doing the boundary map first and then the sharps is equal to doing the sharps and then applying the boundary. What one can conclude from here, by the way, this concludes the proof. What one can conclude from here is actually pretty useful. So the first thing that one can say is that F sharp takes cycles to cycles. And it takes boundaries to boundaries as well. That is the first consequence. To see that that's the case, notice that if you take a zeta in the cycles of k, then applying the boundary in L to F sharp of zeta is the same thing as F sharp of, and this is F sharp of 0, which is 0, which then shows that F sharp of zeta is also a cycle, but now in L. So being able to swap these two tells you that if something started as a cycle, when you applied F sharp, then you end up with something that is also a cycle. So that's this part, this first statement. F sharp takes cycles in K to cycles in L. And now for the second part, is that if beta is in, beta is a bad letter here. If eta is in Bn Kz, meaning this is a boundary in K, then that means that is of the form delta n plus 1 in K, psi for some psi in the n plus 1 chains of K. Right? Because those are what the boundaries, that's what the boundaries are. This in turn implies that if I apply F sharp to eta, then that is the same thing as applying F sharp to delta n plus 1 K of psi. And that is the same thing as delta n plus 1 L of F sharp of psi. And I've shown that F of eta is delta n plus 1 of something. So that shows that F sharp of eta is a boundary, but now in L. right? So it sends boundaries in K to boundaries in L. Um, so let me draw a picture because this is getting confusing by the minute. Um, so here's what we have. We started with our simplicial complexes and a simplicial map between them. Then we created from that this family of sharps that go from the level of chains to the level of chains, but now in L. And if you draw a picture of what this looks like, then here you have the boundaries, and here you have the cycles. And here you have the boundaries, and here you have the cycles, but in L. What we've shown is that the sharp is going to send boundaries to boundaries, and it's going to send cycles to cycles. Okay. So now, and all of that is coming from this condition. All of that is coming from here. So now, let's say that we take two cycles in here, zeta and zeta prime. Okay, and let's say, let's see what happens to their homology classes through F sharp. So I have, I have zeta and zeta prime, so I can think of their homology classes in here, namely whether or not these two guys differ by a boundary. I can look at the sharps of these guys, and I know they're going to give me some cycles. So let me enlarge the picture a little bit. So here is F sharp of zeta, and perhaps here is F sharp of zeta prime. Okay, so I can ask the question, how do the homology classes in here compare to the homology classes that they came from? In particular, I can ask, if these two guys are homologous, is it true that these two guys are also homologous? So let me do that here. Okay, so the second consequence of this is that if zeta and zeta prime and z and kl, kz are homologous, that means that, just to remind ourselves, that means that the difference is a boundary, or equivalently, the homology classes are the same in here. Then F sharp of zeta and F sharp of zeta prime are homologous in Zn of. So F sharp is taking homologous cycles to homologous cycles. Okay, what is the proof? If these two guys are homologous, it means that they differ by a boundary. So zeta minus zeta prime is equal to delta n plus 1k of some psi. And now if I apply F sharp on both sides, I get that F sharp of zeta is equal to minus F sharp of this guy is equal to F sharp of delta n plus 1k psi. But now you can flip these two. And this is delta n plus 1 L of F sharp of psi. Right, so I showed that the sharps also differ by the boundary of something. Okay. So we are done, even though it doesn't appear that we are. So let me do it. Let me do it over there on the right. So I'm going to end with that definition. I'm going to let F star go from the homology of K to the homology of L. And what it's going to do is it's going to take the homology class of zeta and I need to produce an element in here. I need to produce a homology class in here. So what do? First, I apply sharp to zeta, and then I take its homology class in here. So this is the homology class of F sharp, zeta, and C and L. So that's the recipe. The recipe is, how do you go from the homology of K to the homology of L? Well, you start with a simplicial map. Then F star goes from the homology of K to the homology of L. And what it does is it takes a class in here. It looks for a representative, zeta, and then it applies sharp to that representative and then takes the class. So it sends a homology class in here to a homology class in here. And we found a way to compare now homologies of different simplicial complexes, starting from a simplicial map at the level of K and L. The last corollary that we proved that if I take two guys in here that are homologous, then their sharps are also homologous, tells us that this F star is well defined, meaning that the thing that I get here on the right does not depend on my choice of representative. Meaning that if I pick another zeta prime, like there, another zeta prime that is in the same class, then I'm gonna get the same thing here. Okay? So that's how we do it. In these last 5 minutes, let me tell you of how we're actually gonna apply this machinery. The first application is gonna be to clustering, which is a data science problem that people care about. So what is the example? We're going to do a baby case first, and then we'll do the bigger one. So suppose that your simplicial complexes K and L are just two vertices like that. and L is the two vertices plus this edge, tau 1, and that my F is going to be the inclusion of one into the other. Okay? So this example is sort of tracking connected components. Okay. So what happens when I compute H0 of K, and what happens when I compute H0 of L? So again, what do we have to do? We have to look at the zero cycles, right? So each one of these is a zero cycle. And then we have to mat out by the boundaries, but we don't have any boundaries because we don't have edges. Okay. So what is this guy? This guy is just the class of U0 plus m times the class of U1, and then here n and m are just integers. Correct? In other words, this is just Z cross Z. Right? We have two copies because we have two different connected components. Okay, now here, when I compute the homology of H0, what should the answer be? The answer should be just Z, because I have one connected component, and then the homology is going to look like the class, like L times the class of U0, right? But the class of U0 is exactly the same as the class of U1 because they differ by this boundary. So this is the same as L U1, and this is for L in Z. Okay? So if you think about it, when I go from here to here using F star, what I'm doing is I'm sending the class of U0, and I'm sending the class of U1 to the class of U0, which is exactly the same thing as the class of U1. Right? So he's saying that these two connected components merged when I went to L because this edge connected them. And that is something that you can see at the level of homology and at the level of F star. Again, if you look at what F star is doing, it's going to send this guy U0 to U0, and it's also going to send U1 to U1, but these two are equal. So it's as if it were sending, 1, 0 to the number 1 and 0, 1 to the number 1 as well. So that's what F star looks like. Okay, so this is helping us track when different connected components get merged, right? Because something like this will happen. So what would be the application? So the application is, of course, clustering. And the idea is, perhaps you have a data set that, separates into two different clusters like that. Okay. So what we can do, right, is we can look at the Rips complex. Let me say it like this. Perhaps we can look at several scales where we're not sure what the right scale is. We look at the Rips complex at each one of those scales. Right? And then we look at homology in degree 0, just like we did here. So H0 and so on. And then what we would hope is that, at first I would get a bunch of Z's, one per each point in the data set, but then hopefully they start to merge as start to increase the radius. Right? So the cool thing is that the same idea doesn't work. The same idea works indeed, not only for clustering, but we can start to think about how to track the homology in higher dimensions. So I'm going to give you a homework for Wednesday, something to think about. So consider the following simplicial complexes. So K0 is going to be this square, pretty simple. K1 is the square. I'm going to add this edge. K2 is, I'm going to add the two simplex here, and then K3 is going to be the fill-in complex. I am also going to compute homology, but this time in dimension 1. Okay? So here I should get Z, okay? And it's going to be generated by this cycle zeta. So say that, I think that's clear enough. In this side, I'm going to have this generated by this cycle that I'm going to call zeta 2, and this cycle that I'm going to call zeta 1. In here, I should have a Z because this cycle zeta 2 has been killed. I have filled in the hole. And then here I should just get 0 because there are no holes left. Okay? Now, the maps, the simplicial maps I'm going to take are going to be inclusions. My question to you is, what do the F stars look like? In other words, where does zeta go here? Convince yourselves that zeta 2 in fact goes to 0. But again, the main question is to see where does zeta go in here through F star. So this will require you to think about, again, what are the definitions? How are these stars defined? And then what do they do to these generators that I drew in here? Great. So that's everything for today. See you on Wednesday.